Okay, sorry about that. So here I have this LR circuit, and I want to know what is the equilibrium current. As I said, that should be really easy. It should be 6 amps. The reason is, remember, as your current is increasing, it goes from 0 up to 6 amps. This inductor impedes the flow of the current, because you'll get a magnetic field, an increasing magnetic field in this inductor that will cause an EMF to go in this direction. But at some point, the changing nature of that magnetic field just goes down to 0. So here, the magnetic field in this inductor, so I can characterize as dB dt, this approaches 0. And when dB dt goes to 0, that means it no longer produces an EMF. So at some point, that inductor just becomes like a wire. It no longer generates a changing magnetic field, and so it no longer generates an EMF. So the equilibrium current occurs when that inductor acts like a piece of wire. And when it acts like a piece of wire, well, it's just a very simple circuit, 12 volts, 2 ohms. I equals V over R, or 6 amps. Now I want to know, how long does it take to reach that current? Well, let's look at B. So if I think about this, I is equal to the EMF over R. That's my maximum current, times 1 minus e to the minus t over tau, where tau is the time constant of this circuit. It's equal to L over R, and in this case that's equal to 3/2 of a second. Now if I try putting in something, you can try doing this in your calculator. If I put in 6 amps equal to 6 amps equals to 1 minus e to the minus t over tau, you'll find that you get an error when you try to solve for t, right? Because this is an exponential function. If I plot I versus t, the graph looks like this, right? So it slowly approaches that 6 amps, but it never actually reaches it. So here you would get t is equal to infinity, that it would never actually reach 6 amps. So this is sort of a trick question because it never ever reaches 6 amps theoretically. But in practice, it does reach 6 amps. Now remember our capacitors where we had a time constant as well? It looked exactly like this, looking at the charge on a capacitor, and we said that after 10 tau, it's fully charged, right? The same is true here. After 10 tau, this function approaches its maximum value, and we can say for all practical purposes that it is at its maximum value. So at 10 tau, just like we have for capacitors back when capacitors were charging, 10 tau, which tau here is 3/2 of a second, so this is equal to 10 times 1.5 or 15 seconds. So let's try this now with 15 seconds. If I do I equals 6 amps times 1 minus e to the minus 15 over 1.5, I find that I is equal to, well, is equal to 6 amps, 5.99999 or whatever. Okay, so we can use that same general guideline that inductors will stop inducing an EMF after they have reached 10 times the inductive time constant tau L. All right, C, I want to know now how long does it take to reach 1/2 of this equilibrium current? So I'm looking for what is T equal when I equals 3 amps, because the maximum current is 6 amps. What does it equal when it's equal to 3 amps? So I just say 3 amps, just looking at this expression right here, which you have on your equation sheet. 3 amps equals 6 amps times 1 minus e to the minus t over 1.5. You'll need to make sure that you can do this in your calculator. I have a 1/2 minus 1 equals negative e to the minus t over 1.5. This is negative 1/2 equals negative e to the minus t over 1.5. Get rid of that. I take the natural log of both sides. The natural log on this side just gets rid of this, and the natural log of 1/2 then is equal to negative t over 1.5. And so t is equal to the negative of 1.5 times the natural log of 1/2 If you put that in your calculator, you find that it's 1.04 seconds. So that's the answer. Be able to solve this equation. Make sure that you can do that. Number 5. I will pick back up with number 5 in just a little bit.